What are the energy needs of industry? They can be they're typified by 3 points. They're very diverse in requirements. So industries require energy for a wide range of processes, from powering heavy machinery to providing heat for various industrial processes. This will be, of course, the topic of today's webinar. They also classified by high consumption levels. Industrial sectors are often the largest consumers of energy, and they require constant and reliable power supply. The industries also have a changing demands. As technology evolves, industries' energy needs are constantly shifting, necessitating flexible and adaptable solutions. To look more closely on industrial process heat, the industry sector in 2022 was directly responsible for emitting about a quarter of global energy system CO2 emissions. If we look at the first bar and the global final energy demand, industry was using around 40%. And in terms of the industrial energy demand by use, around 55% of this overall use goes towards generating heat for its processes. And at the moment, more than 75% of this heat is generated by fossil fuels, so oil, coal, and natural gas. And only a small fraction comes from other sources, renewable sources also, so biomass, district heating, and electricity. The industry sector is currently not on track to align with the net zero emissions by 2050 scenario of International Energy Agency, and it's even projected that the industrial heat demand will expand 16% globally during the next 5 or so years, with China and India together accounting for more than half of the growth. And these are, of course, all statements from IEA. When talking about industrial heat, the industrial heat is often classified into 3 categories. So we have a low category that's lower than the temperature is lower than 150 degrees Celsius. Some areas or sectors classified falling under this category are in chemical, food and beverage, and papers industries for processes such as drying, evaporation, pasteurization, baking, and sterilization. Then we also have a medium category with temperatures between 100 and 400 degrees Celsius. We have a biofuel production in this category, for example, so distillation to separate impurities, but also textile sector, heat treatments, such as processes such as dyeing and finishing, as well as in specific drying processes. And then we go to heavy industry with high temperatures above 400 degrees Celsius, with the highest emitters or the highest CO2 emitters, such as iron, steel, aluminum, and cement production, also turning hydrocarbon into plastics and other petrochemicals, and high temperature hydrogen electrolysis. Going back to the low category, the lower than 150 degrees Celsius, that's a categorization by IEA, but I would also like to point out that this categorization is a bit blurry because, for example, Joint Research Center of European Commission consider low category as lower than 100 degrees Celsius, so you can see different numbers here. What zero emission solutions are there for industrial heat? As I already mentioned in the agenda, we will today focus on bioenergy, solar thermal, concentrated solar thermal, geothermal, and heat pumps. There are also other options, district heating and cooling, wind, solar, combining wind and solar with storage, and also hydrogen, but we will mostly focus on the first 5 in today's webinar. So without further ado, I would like to give floor to my colleague, Nicolas de la Vega, Policy Manager at HUREC, to give us an introduction on Net Zero Industry Act.
This is the EU's efforts to bring about an industrial policy. So I would put this in contrast, for example, with the Fit for 55, the 2030 framework of the EU, where there are objectives to deploy clean technologies. So we have many targets in Europe, and there is quite a bit of experience in putting sectoral targets, but there was never a prioritization of domestic production. So what this Net Zero Industry Act tries to do is to steer the production and deployment of the green transition towards specifically fostering domestic technologies. So people often compare it to the Inflation Reduction Act in the US, and also China's strong industrial policies. So the main aim of NZIA, or the Net Zero Industry Act, is to scale up net zero technologies, so a specific group of technologies, and have the EU manufacturing at least 40% of its technologies. So this is the objective by 2030. So the concern is that at the moment there are some strategic weaknesses in the European economy, and that's as the transition runs up, there's a risk that Europe will go from being a net importer of fossil fuels to a net importer of clean technologies. So NZIA is essentially a group of public interventions to try to boost specific sectors. I have included in the bottom half of my slides a few landmarks of by when this will start working. So the entry into force was this month, and there will be different things that will be applicable from the coming couple of years. So NZIA, this regulation touches upon permitting procedures for renewable energies. It also looks at auctions. It looks at support schemes. It looks at public procurement. Also looks at skills. So there are quite a few topics, different interventions where it expects to support and foster European manufacturing. Here includes not all, but what I thought were the most relevant technologies covered by the Net Zero Industry Act. Some people might say that there are too many. That was in the negotiation, the box expanded. Still, I think it touches on all the essential clean tech industries. So we have renewables, and especially the sectors that you have introduced today, Andre, the technologies that this group is covering. So we have solar thermal, heat pumps, geothermal energy technologies, biogas and biomethane as well, but also several other enabling technologies like battery, hydrogen. We have alternative fuel technologies, so power to X, and several other transformative industrial technologies also working on industrial processes. But it also covers nuclear fission, for example, wind, solar, and several others. So all these technologies are eligible under the interventions of NZIA. I would like to go through a few three elements that I think could be quite useful for renewable technologies in general, but also for industrial processes. So one I wanted to introduce is Article 26 on renewable energy auctions, and this article requires that at least 30% of the total volume of renewable energy that is auctioned, that 30% of it is done under non-price criteria auctions. So the idea is that generally auctions are taken by the lowest bidder, but the idea here would be that there are other requirements that to foster to develop specific kind of technologies. Generally, there's a limit. Usually, the text considers that beyond 15% of additional costs compared to a normal auction, then a country might say that the costs are disproportionate. But this is up to one country or another. And the criteria that are set here, so these are qualitative criteria, are first of all a resilience criteria. So in an auction, the idea would be that that a country shows there's a technology, the bidder that takes it has a specific type of technology that boosts the made in EU or reduces imports. So it can be material substitution by, for example, imported goods by more locally produced goods, or simply using less imported material, just using less and to be able to do more. So this resilience criteria is a requirement, a fixed requirement in all non-price criteria auctions. And in addition, at least one of the following three. So either a sustainability criteria going beyond minimum legal requirements. So the idea is not to do what the basic legislation says, for example, on eco-labeling, eco-design, sorry, but that or the birds directive or the habitats directive or the water minimum requirements of the EU, but really going significantly beyond. Also, there's a criteria for innovation. So really here, providing an entirely new solution or improving state-of-the-art solutions. So this will be innovation tenders. Some countries have it, but here it's introduced a bit more specifically. So this can be for new technologies that have not been deployed yet, or completely new applications. For example, solar thermal in industrial processes at higher temperatures, I think is something that would be supported by these auctions. And the third one is energy system integration. So this is more about grids and storage. But I imagine, for example, for concentrated solar power and more storage related technologies, it can be quite interesting. There is an implementing act that is being prepared. It's expected to be ready by January. So this act will develop on this non-price criteria. So for resilience criteria, for environmental, innovation, and energy system integration, all the four. And I think if there are interest in this, please let me know. I would also be quite curious if you see this as an option, not just for electricity. Auctions are usually renewable energy auctions are electricity based, but could this be used for heat auctions in a more widespread way? And if so, I think it will be interesting that this goes into the implementing act. Here I have an example of sustainability criteria. So one of the four criteria just mentioned in these non-price auctions. And you see on the left column, this is for PV. It came from the European Solar Industry Alliance. And for example, they include reducing carbon footprint of PV modules, or increasing the yield, or recycling modules more effectively. So increasing the lifetime of a product. So all these things would be considered sustainability criteria, and I think some of them would even could also fit in the resilience elements. So this is just one example for one technology, but I think it would be desirable to have more examples for more technologies, so that the policymakers can make better auctions designs. Two more points. One is regulatory sandboxes. So this is something that already exists in some countries, but the idea now is to have a more of a European framework, and also that countries exchange more on sandboxes. The idea is that countries are more active in trying new technologies in an easier, less regulated way. And just a few seconds on the last one, there's an article 27 on pre-commercial procurement and innovative public procurement. And here again, some countries have them, but not all. And the EU ENSIA tries to boost this a bit more. Also encourages countries to use EU funding to support them. There are no specific targets on this, but the framework is there and is available. And if you see any opportunities with any of these instruments, please let me know. This is a first take. Thank you.
Thank you very much, Nicholas, for this very brief introduction to the Net Zero Industry Act, just to have an idea of the effect it might have on the renewable energy technologies for industries. We would now go into examples from industry. So we will have 5 presentations on 5 different technologies or technology sectors. Start with Wolfgang Gruber-Glatzel from IE. Yes.
Okay,
so Wolfgang, I would give floor to you to talk about solar heat for industrial processes, net zero solutions in practice.
Okay, yeah, thank you for the opportunity to present solar thermal, solar heat for industrial processes as part of one technology, what we've seen for the Net Zero Act, and showing some solutions in practice. Short introduction of our institute. We are an independent research organization in Austria with around 75 scientists working on renewable heating and cooling solutions for industry, communities and cities. Myself, I'm in the industrial systems department, so working on solutions for industries. Our slogan is idea to action, so we bring innovative solutions into practice via research and development, demonstration, but also consulting and knowledge transfer. We have ongoing activities in Southern Africa and via UNIDO to other organizations, other countries in different continents. Myself, I will focus on the non-concentrating collectors. But of course, solar thermal is a bit broader. It's also covering concentrating collectors. This will be presented in about 10 minutes or 20 minutes, depending on the order, by DLR. So more than the concentrating collectors. I can bring the latest statistics on SHIP. You may have seen that the Solar Heat Worldwide report has been published, I think 2 weeks ago. My former CEO, Werner Weiss, is the main author of this report for many years. And what we see and myself, I'm doing the statistics on the SHIP, so solar heat in industrial processes chapter. And what we see if you look at different types of collectors, that we have non-concentrating collectors having the higher number of systems, but the concentrating collectors have more installed capacity. So what this means is usually larger systems are installed with concentrating collectors. What was interesting that around 1 year ago, Soliki published an outlook for the overall sector, and there we've seen for 2023 an expected installed capacity of 71 megawatt for SHIP. So both concentrating and non-concentrating collectors. In the actual report now, Solar Heat Worldwide report, in the actual statistics, we see that actually 94 megawatt have been installed. So an overachievement of the expectations. The outlook for 2024 to 2026 is around 260 megawatts. So we hope that we can also overachieve in this area. What is interesting is that the stationary or concentrating collectors have had a higher share in the past, but the outlook is more towards concentrating collectors. The second trend, which is also interesting, is that heat delivery contracts will dominate the future SHIP market. And I'll also show the examples where this is true, that instead of buying the collectors, industries will buy the heat by a third party that operates the system. So giving you some examples, one is not in Europe, but also delivered by a European company, which is Solid, an Austrian company that is an expert in solar thermal systems. 4,000 square meter of installed flat plate collector capacity, only a quite small storage required in this case, 106 cubic meters, integration directly at the processes. So what was very interesting at this project and why I'm showing it is that it was not that they simply put in the solar system, but also engaged with the industrial client and tried to understand their needs. And they had a very inefficient steam system, calculated steam efficiency from burning fuel to delivering steam of around 55%. So by establishing a parallel system, a parallel hot water system, it was not only about solar heat delivery, which is very efficient, but also about an overall increase in energy efficiency for this industrial client. Currently, they have a solar fraction of 60%, and they're working on the second phase to improve this furthermore with additional collectors and also hybridization with heat pump solutions. A second example is a bit 3 years old, but still very relevant. It has been mentioned even today that around the 400 kilowatt system by TVP is also an Italian European manufacturer. High vacuum flat plate collectors that can achieve quite high temperatures, 155 degrees in this case, at a higher pressure. There's an indirect steam generation, so the solar system actually produces hot water, but then steam heat exchanger can provide steam to the sanification, sterilization, and bottle warming processes in this case. So it was a very good example in showing what also non-concentrating collectors can do in higher temperatures. Well, again, a recent example, a very large example, I think it is the largest in Europe now in terms of non-concentrating collectors, but there's a new one in concentrating collectors. Anyway, this is the largest in France for sure. This is a 10.5 megawatt installed thermal capacity. This project has been developed by New Heat, and this is also a heat delivery contract project. So New Heat has installed this large collector field and also the 3,000 cubic meter storage, a turnkey solution, and provides then heat to the industrial client, which needs to dry the whey for whey powder production. So for the industrial client, there is not the upfront investment needed for the very special installation. They can still focus on their core business of producing whey powder, and New Heat delivers and operates also the whole solar thermal plant and make sure it runs for a long time. Solar thermal has a very low levelized cost of heat in the right environment. So we see successful examples having quite a low levelized cost of heat, around 20 to 40 euro per megawatt hour for projects with quite low renewable fraction. So it's what this graphic is showing is a function of renewable fraction from around 25 to up to 100%. And solar thermal can hardly be a 100% solution, except for very large storages and so on. But it's a very cheap and easy to implement and very efficient, both in land area used and also energy efficient solution that can be part of the solution together with increased storage size, but also in the combination with heat pumps and other solutions. In a fact sheet we developed together with Solar Heat Europe for CEPI, which is the industry association of the paper industry, we have shown that very competitive levelized cost of heat prices can be achieved for different regions in Europe. To sum up, the benefits of solar, and to be also to be frank and to really see how it is. It does have a very high area utilization. So square meter of available land turned into megawatt hours of heat is very efficient. It can have a very low and stable long-time levelized cost of heat for the industrial client. And on a, not for industrial clients, maybe that's not so important, but on a policy level, that's very important that we have a high share of made in Europe products. There's resilience and value added for the European economy if we build on solar thermal. There are challenges for the solar thermal market, not necessarily for renewable in general, because we also do a lot of heat pump projects. So we know that there's a competition with PV on the land area and also competition with heat pump as a solution. But together, it's also, can be very good solutions. The awareness on solar thermal as technology is still surprisingly low. We see this repeatedly again. The high upfront investment is currently tackled quite well with the trend towards heat.
We would now move to concentrated solar thermal. I would like to introduce Peter Heller from the DLR, and he will be presenting on CST technologies for process heat application in industry. So Peter, please, the floor is yours.
So thank you for your kind invitation to share these experiments here for, let's say, different technologies and so on, and for especially for process heat applications. My name is Peter Heller from DLR, German Aerospace Center. I'm the coordinator of the CST for All project, and this is an coordination and support activity financed by the EC. So I talk with my focus of today about process heat application, but I just wanted to introduce you also to our goals and some activities we have in our projects. So in the former presentation of Wolfgang already, we have seen already a lot of details. I give you a short overview on the project objectives of CST for All. So we want to support to create strong and sustainable networks between the different technologies that are relevant to CST, so for the concentrating solar thermal area. We are working for cooperating between the different ATIPs, implementation working groups, and all the stakeholders, and supporting the set plan, implementation plan. So our main activities are to connect or interconnect the different areas that are somehow relevant for our technology. And I'm going to the next slide, which is the workshop that we are organizing in our project CST for All. So we have two different types of projects, industry workshops. Here we have organized one for the hybridization of CST with PV, and one for CST with biomass already. I don't know how many of you have been present in that last workshop. Then we have organized the R&I workshops on cross-cutting materials challenges last year in November, and one on R&D challenges for the hybridization of CST with other renewable energy technologies, so general hybridization topics. We are now organizing one on meteorology, especially for the technology CSP, PV, and wind energy, which are of interest. And also for another workshop for the future energy mix with 100% decarbonation level. You see, these are all organized in this autumn and in spring next year. DLR is coordinator in Germany. Then there's Estella, the European Solar Thermal Electricity Association, CIEMAT in Spain, Enea in Italy, and Otu Gunam in Turkey. This is a consortium. And in the next slide, I show you a little bit the organization. So the project is in the center. Relevant interactions with the Commission, but also with the different ATIPs and other sectors covered by the set plan. And we interlink also the set plan steering committee with its implementation working group with our project. Now I want to show you some industry examples. So technology that is already implemented in real life. So most of what I show you is from one single technology. You can see the parabolic trough collectors with the absorber tube in the focal line of this collector, allowing us to reach temperatures in the order of 400, 450 degrees. Another technology is towers in Fresnel, and I will show you some Fresnel plants in realization and give you some comments also on towers at the end. Let's go through some of these projects that have been realized recently. So you see the magnitude of level of energy that is provided, and also the share of solar energy in these projects. Here, a brewery in Seville. I can tell you from the picture that it's Heineken. You see that in the upper picture, that it's no secret that it's Heineken in Seville manufacturing beer. And the power plant is a parabolic trough plant of 30 megawatt thermal power. Heat transfer medium is pressurized water at 120 to 140 degrees, even that the solar field is producing 210 degrees. So we have some margin between the use temperature and the delivered temperature from the solar field. There is storage consisting of 8 pressurized water tanks of approximately 70 megawatt hours thermal power or thermal capacity. The annual share is 53% of the heat demand of the factory, which is, for my opinion, already a relatively high number. Project partners are ENGIE as an EPC and seller of the heat, Aztec, Solarlight, and Heineken. As I said, it was recently inaugurated. And another technology is the Fresnel collector technology. You see here, for those that are not very familiar with, you have here the parabolic mirrors, like small linear panels on the ground, and the absorber tube in the linear focus on the top of this array of mirrors. So with this technology, you can also go to higher temperatures than with standard collectors. Fresnel collector have some special characteristic when it comes to the focusing, but this is here not maybe the topic of detail that we should discuss. But the peak power here is 4 megawatt thermal, and we cover like 10% of the steam demand of this brewery here in Valencia. And it's again Heineken, as you can see in the picture, that is here the company that needs this heat. There's a thermal storage of 1.5 megawatt hours. And of special interest is here that this project was developed in a very short period of time, in only 8 months, and around 83% of the components have been produced and provided locally, which is also some of the arguments when it comes to European participation in this kind of energy production. A different plant is Turnhout in Belgium. Here, heat is provided for a chemical plant. The plant is producing adhesives. And here you see the special characteristic and also the challenges when it comes to producing heat in industrial environment. You see that the site is very limited. So when it came to how to design such a plant, it was really the question where to put the collectors in the limited space that was available. So this is always a challenge, that the systems have to be individually designed, and which means also that it's including then a higher degree of complexity when it comes to the design. The nominal output here is 3.5 megawatt thermal, and there's a storage with a capacity of 5 megawatt hours. It's a concrete storage. And the difference to the former system is this is going to higher temperatures. So the solar field provides 380 degrees temperature by a silicon fluid as a heat transfer fluid. Even that the user only needs 280 degrees, but it helps us to reduce a little bit the storage size if we input a higher temperature. So we have a higher margin there. This is the company here is Avery Dennison, and the technology provider Aztec Energy Nest and Campina Energy. Another example is in Turkey, in Izmir, space heating and cooling plant for process cooling. You see again parabolic trough collectors with a thermal power of 3,150 kilowatt thermal power. Here, the heating and cooling is done by a two-stage absorption chiller, which is very different to the former systems. There's a high temperature storage on board, and the use here is for cardboard and collapsible boxes production. Very different in technology is the enhanced oil recovery plant in Oman. You see parabolic trough collectors in glass houses. Here you see in this little picture the collector. It's a very cheap and easy constructed collector because it's protected from the glass house around. The glass house could also be plastic housing, though like a greenhouse. The plant is steam in a one-through concept. There's no storage available, but the energy output is relatively high with 445 gigawatt hours per year. So the daily steam output is 2,000 tons of steam. In China, they are also building now a large system for space heating in buildings. This is an example of the Inner Mongolia. It's a 100% subsidized plant by the Chinese government. You see 93,000 square meters of parabolic trough collectors, a huge water storage container of 66,000 cubic meters at 95 degrees. The field is delivering 220 degrees and it's used for space heating. If you want to have a look on all these examples from industry, process heat plants, you can go to this website here, the Energy Atlas. There over 5 plants are shown. You can select them and look at all the individual details about technology, location, collector type. The last slide I wanted to show you is this Solrico slide that was already shown by my colleague Wolfgang Gruber, with a main message that from 2021 to 2024, the solar concentrating collectors increased their share significantly, from 20% to 77%. So you see for industry heat supply, the concentrating technology is of high interest and has a huge potential, of course. So we will see in the future probably a lot of more plants raising up here. Maybe this slide shows you the distribution over the countries. You see in Europe, Spain and France have the biggest share of capacity actually. But also other countries are now looking at projects and showing or doing showcases with smaller projects. Okay, with this, I thank you for your attention and looking forward for interesting discussions.
So now I would like to give floor to Jaap Koppejan to present the Bioenergy for Industrial Heat 5 full-scale examples.
Yes, thank you, Andre. And if you can, so I think we can go to the next one. First about IA Bioenergy. IA Bioenergy is a technology collaboration program within the IA, and there are about 25 countries currently collaborating here and exchanging information on application of biomass utilization for energy generation. And well, basically, this whole implementing agreement is divided into different working groups or tasks, and I'm personally active in the biomass combustion task, but there are also other tasks involved, working on different technologies, but also on biomass trade and CCS, for example, increasing flexibility. There are different topics. And this particular project on delivery of high temperature heat in industry was a project that was carried out by 5 different tasks, and I was coordinating that. Currently, we are working on follow-up of this project, and because we realize that the application of bioenergy in industry will continue to remain a very important application. So here we see the expectations for biomass heat in industry until 2050 in the net zero emission scenario, and this is expected to grow. So it's a light green part of the bar, and so yes, we expect quite a lot of this. At the moment, you see here which fuels are used in industrial heat. Biomass is just a fraction of it, and we see here that the yellow part of the bar on the left in the left graph shows that most of the heat generated by biomass is used for mild steam production between 100 and 200 degrees centigrades, and also basically mostly in the wood and wood product industry and the pulp and paper industry. That's the right pie chart here, and basically these are types of industry sectors that do have their own residues available. So there it's quite logical to use these residues for their own heat demand, and this is a very common practice. What we see now is that there's a trend ongoing that biomass is also traded more between industry sectors, and it's now being used also in other industry sectors where there is a heat demand that's difficult to fulfill in a rather renewable manner. So why can this be interesting, bioenergy? Well, basically, there are different options, very many different options available, different types of fuels that are available, different technologies, and different types of heat demands. And this implies that you can be flexible in the type of solution for a certain application. And so but the biomass itself comes in many different forms. There are well, different types of heat demands in terms of full load hours and types of or the level of the temperature of the heat that is required. Retrofits for a certain application, and I will show an example of that, can be relatively simple. If you have a gas boiler, it can be that you just replace the burner, and in other cases, it might be more complicated to do a retrofit, but so this can vary. There is also an option, and I must emphasize that there are negative emissions possible. In contrast to other options, bioenergy, I think, is one of the few options where, if not the only option, where you can actually achieve negative emissions by capturing the CO2 that is released from the chimney and storing that on the ground, or using it to substitute fossil-based CO2 in another sector. Well, I mentioned already the tailor-made solutions are needed. So the type of application depends on the type of industry and the specific location of the industry to be addressed. I think also in the previous presentation this was already mentioned, but available space may be limited, and this might be an issue also for bioenergy. So there are 5 case studies that show in very much detail how biomass for biomass energy has been implemented as a commercially available, locally available, and also reliable energy source to replace fossil heat. And I will share just one slide for each of these case studies now in the next couple of slides. But on the IA Bioenergy website, you can go through these reports and look at the details. So the first one is a case where natural gas-based process steam generation was replaced by process steam that is generated from locally available residues. You can see here on the left bottom side a picture of the fuel that is used here, a very low-grade type of wood residues from a composting process. So it's the sieve overflow from composting, the very low-grade biomass that is available for free, and it can be used in a dedicated boiler for that's used for at least 7,000 full load hours per year. So here you have an option for a relatively expensive installation, but with a very cheap fuel. So you can use that for continuous steam generation, very reliable and ideal for 24/7 operation. This is a case where a paper industry in the Netherlands also has been equipped with a gasifier, where paper rejects are now being used. You see here on the bar chart the savings in terms of waste disposal, natural gas use, primary energy use, and CO2 emission, and the cost for energy, for water, gas, and electricity. What you see here is that also the gasifier here is used continuous operation to replace the base load for natural gas in this case, while at the same time avoiding costs for waste disposal. So the knife cuts on two sides here, and I think it's a good commercial application. But this is a dairy industry also in the Netherlands, but that's a coincidence. They did have very limited space available on site, and they decided to replace one of the burners in a natural gas boiler with a burner that is fired with fast pyrolysis bio-oil. So this is oil that is produced from wood residues that are then pyrolyzed and using a special process and converted into a liquid bio-oil that can then be brought on site in a local tank and then simply burned in the same boiler. So this is a situation where you have limited space available. This creates a flexible option for heat generation. It is an expensive fuel, so the fuel is about 18 euros per gigajoule, but the investments are relatively low. So this is a high OPEX, low CAPEX option. So you can use this whenever you need the heat, and it's not needed to be operated in baseload. And redundancy of the heat delivery is done in the same boiler. So investments relatively low. This is an example from Sweden, where a paper mill is equipped with a waste incineration boiler. So waste from Norway, from eastern Norway, is burned here in this mill, where steam is generated from the waste, immediately leading to a lower CO2 emission, and also it improves the air quality in the neighboring village, as it also, using this project, also district heating was coupled with the same boiler. So at the same time, waste to landfill was also stopped in Norway. So it again, multiple benefits from the same project. This is a bakery in Switzerland, where I think this is the largest bakery in Switzerland, and here also wood residues and grain residues from the bread baking process are used as fuels in a special boiler where thermal oil of about 300 degrees centigrade is being produced, and this is then used to bake the bread. It's also a commercial project, and there were some issues with the boiler in terms of ash-related project, ash melting, but they were solved in the end, and it's also a good example, I think, of how it can be done. So some takeaway messages. There are different options available, I think, to implement this in industry. However, the option depends on the case. You really need to look at local situation, what fuels are available, what's the heat demand, and which technologies are then most competitive. There are some studies also on the way for the really energy intensive industries, that is steel, cement, etc., where it can also be done, but there immediately you need quite large volumes of biomass, and this might be an issue. So what we see is that particularly the food industries, but also other relatively local industries, they can source the amount of biomass residues that are usually locally available. So that is that's a good advantage, I think. And yeah, you need to do a very site-specific assessment of the feasibility. Well, we are on the way with some additional case studies. These are coming up, and just monitor the side of IEA Bioenergy in the next year or so, and you will see more good examples coming up, I think.
We would now go to the next presentation. We still have 2 to go. I would now like to introduce Guillaume Ravier from ES Geothermy. He will present on the Rittenshofen geothermal plant and illustration of the decarbonization of the food industry.
I'm very happy today to be with you to present you the Rittenshofen geothermal plant. I'm working for Électricité de Strasbourg Géothermie. It's a subsidiary of Électricité de Strasbourg. And this geothermal project was done in the framework with an industrial project, industrial starch plant called Rocket Frères. They have a starch plant located on the Rhine River in the northeast of France, close to Germany. And this starch plant is transforming every day about 2,000 tons of corn and wheat. And for this transformation, they need a lot of heat, about 80 megawatt of heat. And the first cost for this starch plant is for sure the corn and wheat, but the second cost is the energy. So they are trying since a long time to reduce this cost, and they start with biogas because they have a lot of residues on site, so they can transform it into biogas. In 2012, they started and commissioned a biomass plant, a wood biomass plant. And since 2016, they are also using geothermal energy, and we will focus with this part, which is represent about 25% of the heat demand of the starch plants. The Yperngraben, where the plant is located, is part of the European seismic system. So it starts from Basel, more or less, and in Frankfurt. There is a lot of geothermal anomalies with geothermal gradients where the temperature can reach up to 100 degrees C per kilometer. And in this geological area, there is some fluid circulation in nearly vertical fractures, and the reservoir is mostly composed of Muschelkalk, which is Bunsenstein and Carboniferous granite. And in these fractures, we can find a geothermal fluid, a very salty fluid, because it's about 3 times the sea concentration, about 100 grams per liter, and it's mainly sodium, calcium, potassium, and chlorine. So at Rittenshofen, we didn't drill the well directly at Banheim, where the starch plant is located, because the reservoir was really too deep, and we had too much information about the geology. So we decided to drill 10 kilometers to the west in an area where we knew that we had a thermal anomaly, and that's why we drilled at Rittenshofen and not Banheim, because the risk was lower in terms of resource compared to the Banheim site. So the geothermal plant has 2 wells, 1 production well and 1 injection well, and the reservoir depth, it's about 2.5 kilometers deep. For this plant, the reservoir is mainly fractured sandstone and carboniferous granite. So here you have a nice view of a core from Soulsouforêt, and you can see a granite alterated by geothermal brine circulation through some faults. Here there is natural faults which were sealed by carbonate and silicate. So in the case of Rittershofen, the bottom hole temperature is about 177 degrees Celsius, and the total salinity of the brine is 100 grams per liter, and there is also a bit of non-condensable gas, like nitrogen and methane, which represent about 0.2% in mass. So the geothermal plant is designed with one primary loop and one transport loop because the geothermal brine is too salty to be transported from the geothermal plant to the starch plant. So that's why we have two loops. And the geothermal loop is designed with a downhole production Landschaft pump. This pump is designed to increase the production flow rate, but also to pressurize the geothermal brine up to 25 bar in order to keep all the non-condensable gas dissolved in the geothermal brine. So in operation, this geothermal plant has no non-condensable gas emission. So that means there is no CO2 emission in operation. There is a series of 12 heat exchangers to transfer the heat from the brine to the transport loop. And the total capacity of those heat exchangers is about 27.5 megawatts. Here you have a view of one of those heat exchangers. They are tubular. And the plant is also designed with a district heating of 15 kilometers long from the plant to the starch plant. And we are using two kinds of technology for the heat transfer. For the hot line, we are using piping pipe system, and for the return line, it's more classic for the district heating animation of the plant, if it's work, yes. So we are pumping the geothermal brine with the pump, and the brine is directly sent to the heat exchangers, and after the heat transfer, the brine is reinjected into the reservoir. And in the secondary loop, after the heat transfer, the heat is sent to the starch plant with a pump. And at the starch plant, we are generating low pressure steam using the energy also for air dryers and the low temperature used for process heat exchangers. So this geothermal plant is providing about 180 gigawatt hour of heat per year. And we can produce low pressure steam, and we can also use the energy for drying process and low temperature process. We did an intensive life cycle assessment for this project. We applied the ISO standard of course, and we also used the guideline proposed by the GeoEnvit project, which was a research project funded by the European Union. And the functional unit is 1 kilowatt of heat delivered to the district heating. We used the software OpenLCA. The database was the environmental footprint database version 2. And we for this life cycle assessment, we include exploration, drilling, plant construction, operation, maintenance, and of course, end of life. So it's a really full life cycle assessment study. And we came all the results are published in a review called Energies. We investigated 16 environmental impact categories, and we came to the conclusion that related to the gas, greenhouse gas emission, we have about 3.8 grams of CO2 equivalent per kilowatt hour. Casing, cement for the drilling, casing and cement for the plant construction, and electricity for the operation. So there is just one direct emission during the drilling because it was a diesel rig, but all of the rest of the emission are indirect. And in order to reduce this impact in terms of CO2, first all the other industries need to reduce their impacts, and then it's can be also applied for the geothermal energy. We compare this life cycle assessment to the heat produced from natural gas, and most of the environmental impacts are similar or lower to those from natural gas. In terms of greenhouse gas impact, it's about 60 times lower with geothermal energy compared to natural gas. So currently, every year we are saving 40,000 tons of CO2 emission from gas burning with this geothermal plant. And yes, geothermal energy can play a role in the decarbonization of the energy sector and the food industry. and the industry in general when there is, of course, a geothermal resource. There is just one impact which is higher compared to natural gas. It's ionizing radiation, and it's mostly due to the electrical consumption of the pumps. And in France, the electricity mix is based on nuclear power plants, so that's why this impact is higher for geothermal energy compared to natural gas. But with a more renewable electricity mixed, for sure, we can reduce this impact and reach something close to the natural gas.
Thank you very much, Guillaume. Last but not least, we would hear about industrial heat pumps, status and perspectives from Benjamin Zulstorff from Technologies Institute in Denmark.
Yes, so as you said, my name is Benjamin Zulstorff, working for DTI, the Danish Technological Institute, one of the RTOs working with decarbonizing industrial heating. And what we do exactly, to say it very short, we develop technologies, we test and demonstrate technologies, and we support end users in finding their way to decarbonize their processes. So we support the end users in applying new technologies. And I'm responsible for the refrigeration heat pump technologies, which focus a lot on industrial heat pumps, high temperature heat pumps, but this also goes for a number of other technologies such as thermal storages. We also have groups on biogas, biomass, electric systems, and such. The test and demonstration systems, we have laboratories where we actually can test heat pumps here in a megawatt scale in up to close to 200 degrees actually. With that, we are involved in different projects, and among others, we are, so I personally was coordinating the Annex 58 as part of the IEA HPT program. And Annex 58, that was about high temperature heat pumps. And I think this is also how I got asked to give a presentation here. Why is it we are looking at industrial heat pumps? We have heard about different other technologies here. And when we want to find out how to decarbonize industrial heat, then it is a good idea to start looking at the temperatures. We can see here the share of the temperatures or the heat according to the temperatures where it's provided. And we can see that a bit more than 1/3 is provided below 200 degrees, 250 degrees. And this is where we see industrial heat pumps to be very, very competitive. We see heat pumps as very competitive for these temperatures, but it's not only us. It is also confirmed by a number of studies. We're talking about net zero. And if I'm highlighting this one here, then there has been the study, for example, by the IEA, the net zero by 2050 roadmap for the global energy sector. And here I would like to highlight the study where they have analyzed which technologies should be implemented to most optimally reach net zero by 2050. And they have then analyzed, studied the different technologies, and they came to this conclusion here. This is for light industries. And let's look at the low and medium temperature heat demand by technologies. So this means up to 400 degrees, as we have learned also earlier today. And 2020, you can see the distribution of technologies being implemented or which were implemented. It's fossil fuel heaters, some biomass here, and we can also see some electric heaters, and then there's some other heat sources. And the main shift from 2020 to 2030 is that we have this orange one here kicking in. And the orange one, that's industrial heat pumps. And up to 15% of the entire heat below 400 degrees should be covered by heat pumps up to 2030, and around 30% up to 2050. And having this in mind means that it is tremendous numbers of heat pumps which should be implemented here. So this is, again, the main shift from 2020 to 2030 is fossil fuel heaters being replaced by industrial electricity-based heat pumps. There's also some more electric heaters, and I think biomass is also increasing very slightly here. This is, of course, global numbers, and we all know that there are some laggards, and if we want to keep these numbers on average, then it also means that developed countries must go first. So especially in Europe, we see a lot of tendency to go for industrial heat pumps, but also US is having a strong focus on it, Japan, also China. So many things are happening in these countries here. So we have talked about the adoption rate, and if we have this standard, let's say, S-curve for the adoption of the technologies going from research early adoption into mass adoption, late adoption. And we know it takes the numbers from IEA saying that approximately half of the potential should be realized by 2030. Then our curve of adoption would look like this. Millennia growth would correspond to approximately 500 megawatts per month installed. We have been far from this during the last years and months. And this only shows what is about to come if we really want to go for net zero, and what amount of heat pumps we would have to install. And this is, of course, giving a whole different perspective to the installation of heat pumps here. We could see that many of the heat pumps are available at below 100 degrees. Here there are plenty of examples where it's known, where it's commercially available technologies, and where it's preferred heating technology for a number of applications. But we can also see that a lot of heat is actually supplied above 100 degrees. And above 100 degrees, only a few heat pumps had been available just a few years ago. So what we said is, okay, the end users are standing there and they have to decide on how to decarbonize. And it is unclear what technologies, what high temperature heat pump technologies are on the way. So they could not include them in their strategic development for the process heating, because it did simply not know of the developments which were ongoing. And it was maybe a handful of technologies being available a few years ago. So we said, let's gather the technologies which are becoming available, which are available, but also which are on the way to become available in just a few years. So in this Annex 58, we have gathered different technology descriptions. All these technology descriptions are available as 2-page summaries, so very handy, very compact information about industrial heat pumps. It was showing a lot this broadness of the technology where it is now. It's a lot under development. It's a very rapid development. We have seen TRL levels reported from between 4 to 9. We have seen average specific cost between 200 euros per kilowatt installed to 1,500 euro per kilowatt. This also shows a variety of technologies and where they are in there as a market development, let's say, and the commercialization. We have seen a huge range in capacities from just a few hundred kilowatts up to 100 megawatts on a single heat pump. We've seen supply temperatures being reported all the way up to 280 degrees. And then, of course, availability and so on are also some aspects here. So there are plenty of examples available. And if we condense all these to one figure, then this figure looks like this here. So the transition from towards 2030, we have clustered it to technologies below 10 megawatts and above 10 megawatts. Below 10 megawatts, it's more economy of numbers. So many standardized units. They are becoming available up to 120 degrees. They are commercially available up to 120, 160 degrees in this temperature range. Many demonstrators are being demonstrated and tested right now here. Out here at DTI, we're currently testing 2 different technologies, and there are a lot more to come, which we are going to test here. They are going to be expected commercially available during 25, and then for even higher temperatures, there's a bit more delay. There are also systems for even higher capacities, above 10 megawatts. This is typically integrally geared turbo compressors, for example, known from process gas compressions. They're quite advanced, they're available, they are commercially offered, and we are waiting for the first projects here in industries reaching the temperatures indicated. But again, they are typically used at way more challenging applications. So here we believe that they certainly can do the job and be applied for heat pump technologies also. So all in all, there's a rapid development, and it will be a challenge for end users to keep up and to actually use the latest technologies being developed here. So what we do is we suggest that typically it should be a long-term strategy process, or there should be a long-term strategy, which is developed in a process consisting of several steps. These steps, which are included, I'm showing them here. This is what we do in our procedure here at DTI, but other general, let's say, processes do look similar. It typically includes some process mapping. It typically includes the development of concept solutions for one or more sites, for different processes, different level of integration, and so on. It is important to consider what technology is available and what will be developed, become available, because if there's a highly promising technology available in just 1 or 2 years, well, then we can of course consider it in our multi-year strategy to decarbonize. We do a decarbonization roadmap. We de-risk the projects. This could be, for example, by testing it or can also be by having a certain technical due diligence or backup measures here. And then, of course, it is steadily implemented in smaller sub-projects. What is different if we look at heat pump, and we've also heard it a bit for the other technologies, trade-off between process heating or trade-off between OPEX and CAPEX. If you look at fossil fuel-based process heating, the heating is, or the levelized cost of heat is mainly based on the fossil fuel consumption. You pay per kilowatt hour, and this is mainly determining your business case. If you go over to a heat pump, where you still pay your electricity based on the kilowatt hour, but the price for kilowatt hour is depending on the time of operation for the day. So this is a factor to be considered. The installed capacity is a lot more expensive than for gas boiler or so. So here it's important to also consider the capacity, and you're also paying for the temperature. And the higher temperature you need, the more you need to pay in OPEX. But just because there are 4 factors doesn't mean it's more expensive. It just means that you have to have a more holistic strategy to get most out of it. So if I concluded for the market potential, well, when we talk about decarbonization in industries, we hear 2 paradigms, and this is energy efficiency and electrification. And heat pumps are unifying and combining these 2 aspects to reach highest performances. And this shows how important heat pumps are for the decarbonization of industry sectors. We see that technologies are available, and we see that a lot more technologies are becoming available right now. We see that the technologies are becoming more competitive, and the market as a whole is becoming more competitive. We see that the boundary conditions are becoming more favorable. Electricity prices compared to alternative fuels are becoming more favorable with an increasing share of renewables in the electricity grid. We can see that the integration of heat pumps requires a shift of mindset at end users. We foresee an enormous scaling of the supply chain here. And of course, there will be a lot of learnings ahead. When we roll out these tremendous numbers of heat pumps, we will all get a lot smarter and hopefully learn something from it.
Thank you very much, Benjamin. Indeed, you have now completed the examples from the industry of these 5 technology sectors. Maybe I can start with just collecting some statements or ideas from the participants, from the experts. So I gathered from these different presentations that the technologies are geographically and site dependent, and in some cases they also compete against each other. I would like to, maybe if you could pinpoint or highlight some main challenges for the deployment of these technologies, and also how can the European Commission help or assist in overcoming these challenges, and also in the scope of the Net Zero Industrial Act that was introduced at the beginning. Maybe if you could, maybe if you see an opportunity in these regulatory sandboxes or non-price criteria for auctions, you can also highlight that. So maybe we could go with Jaap first.
Yes, I find it hard to say what technologies are most suitable in which sector. I think it really depends on the case. I was quite impressed, I must say, by the alternatives, also progress that has been achieved in high temperature heat pumps. And I think also there are combinations possible sometimes. Like there are sectors where bioenergy plants are traditionally used, like in district heating, where high temperature heat pumps might now sometimes also be a real alternative. So I think, yes, I'm quite happy with this, with the various presentations, and impressed also. I think there's a lot of work to do for everyone, without a clear winner at hand up front, I would say.
Yeah, thank you. Wolfgang, maybe your view on the overcoming the challenges and how can the European Commission support this process?
Yeah, I think we see that we require all technologies in the aim to decarbonize the industry in Europe. I think heat pump, we've seen the very strong development in this area. But also biomass to have here well good usage of the available resources. Yeah. And the combination with heat pump is always the question of not only where we can reach, but also where do we start. We talk about the COP, so it's also about the combination of the right technologies, I think. I think this is a good initiative, the Net Zero initiative, to support also innovative developments.
Thank you, Wolfgang. Peter, maybe if the audio works.
Yeah. let me see if it works. Yeah, thanks. What comes to my mind always is how to get the technologies into the market, and I see biomass as a very promising resource, especially for hybridization with others, like CST is one of the technologies, simply because then we can go to higher power levels or higher or bigger sizes of plants, because then we have two combinations of the combination with biomass and CST is for me a promising candidate, especially for Central Europe, where we can see that biomass has a limited size or limited resource in the area normally due to transportation issues. So combining it with solar, then we can have hybrid plants that can operate 24 hours a day, just with the help of an additional power source that is limited in let's say in volume. This is one option. And what I wanted to mention concerning the Net Zero Industry Act, I think it's very, very important that the political support is not just for one period of, I don't know, 2 or 3 years or so. We need the support, a strategic support for decades, like the Chinese do with their industry policy. If we have a strategic interest in bringing some technology forward, we have to allow companies to gain money with it at the beginning, but then cost goes down with volume and with mass production. And this has to be very much supported by our politics. And I don't see that at the moment, even that there are interests to help, but it's not as strategic as other countries are working.
That's a very good point. Thank you for that, Peter. Guillaume, maybe you can continue with your view.
Yeah. With the example of the rocket plant at Panheim, there is no competition between renewable energy, because all of them has their own resource and they are limited. And when you are facing with a lot of heat demand, then you need several renewable sources to achieve nearly 100% of the heat. So it's not a competition, it's a combination. And we see this a lot with geothermal energy and heat pumps, where we can use the highest energy for direct use and the lowest with heat pumps. So that really makes sense to combine all the technology and renewable energy sources. And I will also say that we need a very long support in terms of politics, because in the case of geothermal energy, one project is at least 5 to 10 years. So if the politics is changing every 2 to 5 years, there is no long support for the geothermal energy.
Yeah, thank you very much, Guillaume, for that. And also, very nice points. Last but not least, Benjamin, if you have some views to share.
Only a short comment. I don't think there's a lot of time left. So I don't think there's time for detours and finding or trying other things. It's a time to go for final solutions directly and no intermediate solutions here. And this requires a certainty in which direction we want to move. Just as an example, I mean, it can make sense to go for these solutions. We have seen it in Danish district heating, for example. A lot of the power plants have been shifted to biomass to have as a kind of quick fix, and now it's all electrified, so we're going to heat pumps as the next solution, phase out biomass. And I believe when we now talk about industries, there's such a high pressure to go for the solutions that we should go for final solutions directly. But this simply requires that you, first of all, have end users who understand they need a strategic approach to go for it. this is not really business as usual for them. It's different decision making for them, and it requires a solid boundary condition in terms of, for example, electricity prices and other price developments. And this is currently not given. And this simply makes, I mean, we can only convince end users still if there's a business case for them. And we can tell them, yes, electricity prices will be more favorable in future, but then they just wait with their investment decision. And this is increasing, yes, let's say some delay in my opinion, which could be avoided.